Hello, everyone. I'm Brett Psyche, and I, along with Oliver Flatt, will be presenting our work on combining precision tuning and rewriting here at ARITH 2021. So when writing numerical code, we try to minimize two things, error and latency. In gaming, we want to minimize latency as much as possible, so we have a high tolerance for error. On the other hand, in computational geometry, we want to minimize error as much as possible, so we're willing to have slower code. And of course, there are scenarios in between, where we want an accurate result, but we don't want to be waiting around for critical computation to finish. So for any expression or function, we have a Pareto frontier of possible implementations. And the important thing is no one implementation is right for every application. For a particular scenario, we need to search the Pareto frontier and choose the implementation that best fits the workload. So we use two techniques to find these expressions. The first is precision tuning, such as lowering a double to a single. And the second is rewriting, such as taking a series expansion of some expression. So what can we say about these two techniques in general? Well, the goal of precision tuning is to increase speed. By lowering the bit width, we increase caching as well as vectorization. Now, it's difficult to know where to lower the precision of an expression. Past work has shown that delta debugging helps here. And rewriting helps avoid cancellation and allows us to give rough approximations of expressions. For example, if an expression contains x plus 1 minus x, we should just replace that with 1. Now, it's difficult to know where to carry out these rewrites, and it's also difficult to know which rewrites to chain together. And past work has shown that programming language synthesis helps here. So let's look at an example. In double precision, this expression is inaccurate for small x, and it may be slow because of 2 calls to x and 1 square root. So how do we optimize this with precision tuning? Well, to make it faster, we should just evaluate it using single precision. And to make things more accurate, we should just evaluate it with an 80-bit float. Well, how about rewriting? Obvious choice is to simplify. We get this nice, concise, and accurate expression, but maybe it's still too slow for you. So if you take series expansions, you get smaller and faster expressions. Now, in general, it's hard to know if we should choose precision tuning or rewriting. And in many cases, we want to use both. Now, in the past, what you do is you choose a precision tuning tool, you choose a rewriting tool, and you combine them in some fashion. Of course, this raises some key issues. Should we tune before rewriting? Should we rewrite before tuning? Should we alternate? And how do we share data between runs? Well, the obvious fix is to precision tune and rewrite at the same time. And here's an implementation that requires both of these techniques. For small x, we use this rewritten Taylor series or Taylor expansion. And for larger x, we use this rewritten and tuned expression. So what we found is when we combine precision tuning and rewriting together, this allows us to produce a rich set of Pareto-optimal implementations. Furthermore, finer grained interleavings of the two techniques create better Pareto frontiers. And in terms of implementation, we can make precision tuning a rewriting problem, and local error analysis helps guide both of these techniques. So we took these key insights and we made a new tool called Pareto Herbie, or Pherbie for short. It takes an input expression, automatically and simultaneously applies precision tuning and rewriting, and produces a set of Pareto-optimal implementations. So before we get into what Pherbie is, we should talk about the tool it was built from, Herbie, a rewriting-only tool. And Oliver will cover that now.
All right, thanks, Brett. So the key idea is to combine precision tuning and rewriting to get better programs. But before we talk about combining both of these techniques at once, I'll be talking about just rewriting. So for the past couple years, I've been doing work on a tool called Herbie. Herbie automatically improves the floating point accuracy of programs, and it does this using just rewrites, not precision tuning. For example, if you take the program Brett introduced earlier, and you give it to Herbie as an input, it automatically produces the simplified output, which has much less error. And in fact, it does this in the same way that we would do by hand, by applying mathematical identities to transform the program into an equivalent one. We call this rewriting because you rewrite parts of the program into new parts. At a high level, Herbie takes a program P, applies rewrites to it, and produces a program P prime which has less error. To do this, it needs a measure of error. So the first thing it does is sample a bunch of points and measure the error of P on each of the points. Then it applies rewrites to P and produces P prime which has less error. But how does it apply rewrites to P? There are lots of ways you can apply a rewrite to a program. You can apply it to multiple parts of a program, and you can even apply it multiple times to the same program. The general strategy Herbie uses to combat this is to place P in a database of candidates and run an improve loop that iteratively improves the candidates by using rewrites. And so as the improve loop improves the candidates, we generate new programs that could potentially be our final output. But the question is, how do we pick a final output P prime from our database of candidates? Let's take a look at a hypothetical example. Pretend we're analyzing a potential candidate, and we'd like to know what its error is across different parts of the domain. So on the x-axis of this graph, I've shown the inputs to the program, and on the y-axis, I show the error. The red line shows that it has low error on the left side of the domain, and it has high error on the right side of the domain. Let's take a look at another hypothetical example. This time, I've graphed the program's error in purple. This program has high error on the left side of the domain and low error on the right side of the domain. So each of these candidates wouldn't be great alone because they have high error on parts of the domain. But if we combine them, we get a much better program, and this is possible using branch conditions. We can branch across the dotted line by checking if the input is to the left of it and choosing the red implementation in that case, and otherwise we choose the purple implementation for the right half of the domain. Combining these two candidates gives us a program that's much better than either of them alone. So this is the general strategy that Herbie takes. It combines different candidates to get a better P prime than each of them alone. We call the algorithm that performs this transformation regimes. The regimes algorithm is a dynamic programming algorithm that combines candidates optimally given a fixed number of branch conditions. That way, you know that your P prime is the best you could do given the candidates that Herbie found. However, regimes only works well when you have lots of good candidates in the database already. So the real reason that Herbie works so well on programs is this improve loop that I mentioned earlier that iteratively improves the candidates in the database. So let's take a deeper look at that. Here I've expanded the improve loop into multiple phases. The first phase is localize. The job of localize is to target high error spots in a program. It does this by looking at each operator and figuring out how much it contributes to the overall error. Take this example. We want to know how much error the minus node contributes to the overall program's error. The left child of the minus node is a division, so it could result in an inexact answer. But the thing is, we don't want to take into account the error from children when we're figuring out how much a single operator contributes to the overall error. So the strategy Herbie employs is to calculate the exact answers for each of the children and then perform the floating point approximate method of computation to get the actual operator's result. This way, you get a good estimate of how much the minus node, in particular, contributes to the overall error. Since localize has figured out which parts of the program we should rewrite, the next phase is to rewrite those parts of the program. Herbie draws on a database of mathematical rules encoded in rewrite rules to transform the program. Take this example. This is commutativity over addition. It says that you can bind variables a and b on either side of a plus node and transform it into the program b plus a. Applying all these rewrites gives us a bunch of new candidate programs, and we also apply a couple of other techniques like series expansion to get more programs. But after producing so many programs, we need to figure out which ones are good and which ones are bad. Since Herbie optimizes solely for accuracy, we only care about how accurate these new candidates are. So the job of the prune phase is to only keep accurate programs, where accurate means it's the most accurate on at least one point. Keeping all the programs that are the most accurate on their part of the domain is helpful because regimes can then stitch them together later. The general strategy here is to generate a bunch of programs in the rewrite phase and filter them out during the prune phase. After multiple iterations of the improve loop, we send these candidates off to regimes to get combined into P prime. Let's go back to our example. In this case, Herbie finds a good candidate and produces it as a small and accurate program as the output. But the output of Herbie is not necessarily small. And in fact, because it optimizes solely for accuracy, you can sometimes get really big programs. Here's a case where that happened. We have a relatively simple input program, and the output is pretty complicated. Herbie was only doing its job. It produced an accurate program, regardless of the size. But this program is quite slow, and if you needed a fast implementation, this would be a bummer because you wouldn't be able to use Herbie. This would force you to optimize it for accuracy by hand, which would be really hard. So that's one of the problems that Pareto Herbie, or Pherbie, tries to tackle. It generates a wide variety of programs with a trade-off between speed and accuracy, so the developer can pick one implementation that suits their needs. I'll pass it back over to Brett, who will explain all about Pherbie and how it works.
Thanks, Oliver. Now that we have a rough idea of how Herbie works, let's look at how we extended the Herbie pipeline to make Pherbie. So here's the Herbie pipeline, and the main change is we want to use both precision tuning and rewriting to create a set of output programs. So we had to make a few key changes. First, we had to introduce precision tuning. Second, we had to filter by both accuracy and cost. And third, we had to actually extract multiple expressions. So let's first look at how we introduce precision tuning. Here's an example rewrite rule from Herbie. This is a distributive rule. And the key is Herbie only uses a single global precision. That is, if the user specifies double, all these operators produce double precision results. But in Pherbie, we use precision tuning, so we'll create multi-precision expressions. So clearly this won't work. So the fix is to specialize each operator to a particular precision. And this allows us to match on an expression by both the operator and the type. Now, why is this important? Well, we can introduce a new class of rewrites called precision rewrites. These take an expression in precision P and change it to an expression in precision Q. Now, these two classes of rewrites implement rewriting and precision tuning within Pherbie. And more importantly, because we implemented it this way, we can use a lot of the same rewriting techniques as Herbie. Of course, this raises the question, where should we apply these new precision rewrites? Well, Herbie applies rewrites at locations of high error to improve accuracy. So we should take that same idea. We should increase precision at locations of high local error to improve accuracy, but we should decrease precision at locations of low local error to improve speed. So that's rewriting. Once we generate all these candidates, we need to filter them. Now, in general, pruning takes the many candidates that were generated and discards the non-optimal ones based on some criteria. So in Herbie, that criteria is a candidate must be more accurate than every other expression on at least one sample point. Now, will this work in Pherbie? Not quite. Because we're pruning by accuracy, the table will become biased towards slower expressions. One or two term polynomials will probably be thrown out of the table, and we want to keep those. So for Pherbie, we add a second condition. That is, we should only compare against other expressions that are at or below the cost of the candidate. In other words, it'll stay in the table if it is best in class on at least one sample point. Of course, what is cost and how do we measure it? Well, cost is just some measure of the candidate's speed. But what we found is it's very expensive to get precise timing data for each candidate. We'd have to evaluate it many times to get an accurate estimator of its speed. And each iteration, Pherbie produces thousands of candidates. So this just won't be practical. Well, we only really need the relative speed between expressions. So we can just use a simple cost model. And this allows us to quickly estimate the speed of an expression. So here's an example cost model. We assign a cost to each operator. Arithmetic operators get something like 1, while library functions, since they're much more complicated, get something like 100. And we also multiply each operator cost by the bit width of the representation. That is, an add and double is twice as expensive as an add and single. And this is just to model moving bits through the memory hierarchy. Now, we can calculate the cost of an expression by going through the AST and adding up all the operator costs. Of course, there is the exception of conditionals, which we should add the cost of the branch conditions and the cost of the largest branch. Now, in general, as long as your cost model predicts real performance sufficiently, it's good enough for Pherbie. Of course, better cost models exist. If you want to sit down and carefully craft your own, you're welcome to do so, because Pherbie is modular. You can swap out a cost model for the default one. So back to pruning. Since we prune by both accuracy and cost, at each simple point, we have a set of candidates that are best in class on that point. And that set includes the accurate expressions that Herbie would have kept, but it also keeps fast expressions as well as every Pareto-optimal candidate in between. And because we keep this diverse set of candidates at each point, we ensure that the final set of implementations are Pareto-optimal. So that's pruning. Once we run the improved loop multiple times, we should extract multiple expressions, and we should probably use something like regimes to combine candidates. Now, the Herbie regimes algorithm won't work since it only produces a single candidate, and we want to produce a proto-frontier. But we can actually reuse that algorithm and run it multiple times on a subset of candidates from the table. So at a high level, we have a cost bound, and we run Herbie's regimes algorithm on the subset cheaper than this cost bound. For the first iteration, the cost bound is high enough so that we run the algorithm on all candidates. And this will produce an output expression. Then we decrease the cost bound. So in the next iteration, we will produce a different candidate. And we repeat this process until no candidate is below the cost bound. So let's look at an example. Here's the same example from the introduction. And let's assume we've run the main loop multiple times. And now that the table is full of candidates. Well, we should repeat this process until the table is empty. First, we run the regimes algorithm, and then we produce an expression. Then we decrease the candidate table, so we won't produce this next time. And we just step through this process. We produce this nice simplified one, decrease the cost, produce this fused expression, lower it again. We produce this Taylor series or Taylor expansion, and then we finally produce this constant. And finally, we lower the cost enough so that the candidate table is empty. And as you can see throughout this entire process, we produced the final set of implementations that are Pareto-optimal. So that is Pherbie. Once again, we extended Herbie by adding precision tuning, filtering by accuracy and cost, and extracting multiple expressions through regimes. All right, now let's look at some of Pherbie's results on some benchmarks. So we use two main benchmark suites. The first is from Hamming's Numerical Methods for Scientists and Engineers. This is a standard textbook on numerical analysis, full of naive expressions with high error. The second is Physically Based Rendering. This is an open source textbook describing techniques in rendering photorealistic scenes. So here are three examples. The first is from PBRT. This expression helps compute the intersection of curves. And this black square in the bottom right is the error and cost of the initial expression. And all these red dots are the implementations that Pherbie produces. Now, the important thing is that Herbie will produce the implementation in the bottom right, since all it cares about is accuracy. But Herbie fails to find these candidates that Pherbie finds that have a similar error, but much lower costs. In fact, there's this implementation in the bottom left with just arithmetic operators. Here's this other example, difference of tangents. And the interesting thing here is the starting expression is on the Pareto frontier. So if we want to decrease cost, we have to increase error dramatically. And if we want to decrease error, we got to increase costs. And once again, look where Herbie's result is. And clearly, Pherbie finds better implementations. And finally, here's this last example. This expression is used to sample reflections off of rough surfaces. And the key is that the starting expression is suboptimal. That is, Pherbie finds these implementations that have lower error as well as lower costs. So these may be of interest to a user. Now, we made the claim in the beginning that finer interleavings of the two techniques create better Pareto frontiers. So we ran 7 treatments on the two benchmark suites. The first 3 only use one of the techniques. The other 2 chain the techniques together. And the final 2 use the two techniques at the same time. Once again, Pherbie uses rewriting and precision tuning within the same phase, while the coarse grain variant uses them separately in a much less targeted and much slower method. So here are the results from the benchmarks. And these curves answer the question, for a given cumulative cost, what is the minimum cumulative error we can achieve by selecting a single output expression from each benchmark? And the important thing is, in both cases, the two treatments that interleave the techniques together produce better Pareto frontiers than the two treatments that chain the techniques together, or the single technique treatments. So here is the same graph up close. Numerical methods contains high error examples, and that's why we started at a place of high error. Note that Herbie, the orange square in the bottom right, does in fact find better implementations, but increases cost dramatically, while Pherbie finds similar implementations for lower costs. On the other hand, PBRT is real-world code. We start with low error, and Herbie does in fact find better implementations, but Pherbie can pull something off similarly for a much lower cost. So that's the evaluation. Once again, Pherbie does in fact produce Pareto frontiers, and we show that finer grain interleaving creates better optimizations. Of course, Pherbie doesn't exist in a vacuum. Here are just a list of a few publications on precision tuning and rewriting in recent years. And Pherbie, as well as this talk, would not have been possible without the rest of the Herbie development team. Pherbie is the end result of years of hard work and seeing how far we could push, how far we could expand Herbie into other fields. So I'd just like to thank everyone who has contributed to the Herbie project in recent years. So that's the end of our talk. Pherbie will be released in the next version of Herbie, Herbie 1.5. That version will be released in a few weeks, so please be on the lookout for that. Visit herbie.uwpulse.org for more information. Thanks for listening.